activation energy is the threshold energy that must be overcome to produce a chemical reaction. You need this because bonds must be broken and energy is required to break bonds. And if you don't break the bonds, no reaction occurs. A catalyst is a substance that speeds up a reaction without being consumed. It does that by providing an alternate pathway with a lower activation energy. And an example of that would be an enzyme. So EA is activation energy. And a catalyst, when you're given a mechanism, which you'll see later in this lesson, it's going to start as a reactant and then show up later as a product. So you're going to start with it and then end with it. On this picture, you can see a catalyzed and uncatalyzed pathway. And notice that the delta E, or change in energy, is the same for both pathways. Activation energy is measured from where you start to the top of the hill. So we started there, and we're going to have to go all the way up here for our uncatalyzed pathway. And so we can measure that energy if there was values over there to figure out our activation energy. If you notice, for the catalyzed, it's only from there to there, in which case it has a much lower activation energy. But where we start and where we end is still the exact same. On here you can see the effective collisions for uncatalyzed and catalyzed reactions. You have more effective collisions for a catalyzed reaction because you have a lower activation energy. So more molecules have that required energy, so more reactions occur. There's two types of catalysts, homogeneous and heterogeneous. Homogeneous would be the same phase as the reacting molecules, while a heterogeneous catalyst is a different phase as the reacting molecules. And so this is usually a solid that provides a reaction surface. So homogeneous would be like a liquid in liquid, while heterogeneous a solid in a liquid. But it doesn't have to be a liquid that it's being reacted in, it could be a gas or two solids. So go ahead and pause the iPod and try answering this one on your own, and then restart when you've got it. Okay, so our correct answer should be D, which is providing an alternate pathway to the reaction, effectively lowering the activation energy. C would be wrong because we don't increase the energy, it's the same. We aren't going to change it from endo to exo. And A is incorrect as well because catalysts aren't consumed. A reaction mechanism is the steps by which a reaction takes place. It's going to tell us how the reactants become products because they don't usually happen in just one step, which is what we usually write. And they cannot be proved absolutely. So it's just a theory on how the reaction takes place. Before we get to that, there's a rate determining step, and that's the slowest step in a reaction, which determines the rate. Because a reaction is only as fast as its slowest step. And reactions proceed faster at a higher temperature. Increase the temperature, reactions happen quicker because there's more collisions. All right, so you're given this equation and you're given the rate law. And then below that you have the mechanism. Notice that our rate law is NO2 to the second power. In our mechanism, they've labeled the slow and fast step, so the slow step is our rate determining step. You always get the rate of the reaction from the slow step and anything above the slow step. You look at the reactants and only the reactants of that slow step and the things before it. So our rate is equal to K and then NO2, but we have two of them, so it's going to be squared. If you look above that, our rate that was given corresponds to this rate. So we're only look at the slow step and nothing after the slow step. Slow step and what's above it. An intermediate is formed in one step and then used up in a following step. So it's never seen as a product. It's going to be a product and then a reactant. And we need to look at the previous problem and see what the intermediate was in this problem. So you look at your products. NO3 we have as a product, and then we have as a reactant. Nothing else we made and then used, so just NO3 would be the intermediate. An elementary step is a reaction whose rate law can be written from its molecularity. On the next slide, we'll see what molecularity is. All right, so unimolecular is a reaction involving one molecule. Bimolecular is two molecules colliding, and termomolecular are three molecules colliding. In order for a mechanism to be possible, the sum of the elementary steps must give the overall balanced equation for the reaction, and it must agree with the determined rate law. If one of these does not fit, then it's not possible. All right, so they gave us the equation, they gave us the determined or experimental rate law, and here's a possible mechanism. They want to know, is it consistent? So the first thing that we're going to do is determine our rate from this mechanism. In order for it to be correct, it's got to be second in NO2 and first in H2. So here's our slow steps. We've got to look at it and any step up before it. So rate is equal to K, NO to the first power, because there's only one, and H2 to the first, because there's only one of those. If we look, notice that those do not match, and so this is not the correct mechanism for this reaction, because we'd have to have two NOs reacting. And actually, if the second step was slow, then that would have been a correct mechanism, since the N's would have canceled out and we would have had two NOs and one H2 on the reactant side. Okay, but let's just see if our mechanism adds up to our reaction. So cross out everything that is on both sides. So we have an H2 or an N2O and an N2O. And there's a nitrogen and a nitrogen. And so now add them up. And just remember that nitrogen and NO2 were both termed intermediates. So we've got two NOs. And they're reactants, two H2s as reactants. And on the product side, we have two waters and one N2. So our reaction does match, just not the rate law. All right, go ahead and pause the iPod and try this one on your own. Figure out which steps are bimolecular. All right, so the first one is unimolecular because you just have bromine reacting with light, and light's not a molecule. B looks like it would be termolecular, or 4 molecules, but we have 2 to 2 to 2, which could reduce down to 1 to 1 to 1. They just didn't because if we reduced it down, then the reaction wouldn't add up, or the steps wouldn't add up to the reaction. So we had to have B happen twice. So if we put it to 1 to 1 to 1, then B was by, C's by, D's by, and E's by. So the correct answer should have been B as in boy. Go ahead and pause the iPod and try this one. Figure out which ones are intermediates. Okay, so for this we're going to have to cross out each step that is, or each substance that is the same on both sides. So we have 2 bromines. We have 2 HBr, but if we eliminate the 1 in C and D, then we aren't going to have to mess with the coefficient, coefficient in front of B. Bromine, 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 and Br2. In B we have 2 hydrogens, so we can eliminate the hydrogen in C and D. And that's pretty much everything that we can eliminate, except in B we have 2 hydrogens, D we have 1, so we can leave that as just one of them. So this leaves us with C, D, and E as all intermediates. And that's all.